Hey, everybody, welcome back from spring break. Hope you had an awesome holiday. I had a pretty good time. I was a little disappointed at how fast my hair is growing, and there's no barbers around to get a haircut. So I guess I'm just going to have to grow it out and embrace the long hair. I'm sure lots of you are doing the same thing as well. Hopefully, your long hair looks a little better than mine does. Anyway, what we're going to be doing today is gas stoichiometry. Before we do that, so this is a 2-day topic, and it's just a quick little one, and then we're done gases, and we'll be moving on to solution stoichiometry. And I wanted to do one review example of gravimetric stoich, which you guys learned, I don't know, a couple weeks before the break. And this is just to make sure we're all on the same page. So this isn't in your notes. I'm just going to do this question as an example, and you can just follow along. And that way we're all using the same vocabulary and the same methods to attack these stoich problems. So here we go. Okay, I'm back with my real hair. All right, so the question is, what mass of carbon dioxide gas can be produced if 30 grams of C2H2 is burned? Ooh, okay. So anytime you have a question in chemistry and you are asked to solve for a mass or a volume or a concentration, and it's a chemical reaction, you always need a balanced chemical equation. So how do we know this is a chemical reaction? We've got a mass of CO2 that can be produced when we're burning C2H2. So combustion or burning of C2H2 is our chemical reaction. So we need a balanced chemical equation, and I'm just going to do this really quick. So, excuse me, C2H2 is burned. So there we go. Burn means reacting with oxygen. When a hydrocarbon, a hydrogen and a carbon, so a hydrocarbon combusts or burns, you always get CO2 and H2O gas as the products. And when you go to balance this one, two carbons, and two hydrogen, those are balanced. Two oxygen on this side, I have 2 times 2 is 4, plus one more is 5. When you get an odd number on the right-hand side, do you remember what to do to balance this? Because we can't put a 5 over 2 here on this oxygen, so we have to double it. When you get an odd number of oxygens, you double. So 2 becomes 4, 1 becomes 2, 1 becomes 2. So I've got, just verify, 4 carbon, 2 times 2 is 4 hydrogen, and now I have 4 times 2 is 8, 2 times 1 is 2, 8 plus 2 is 10, 5 times 2 is 10. There's our balanced reaction. Okay, we got a balanced equation. What next? So now we're going to be doing stoichiometry. And you need a balanced equation because we need these molar ratios or these coefficients. This is how we convert one amount of chemical into another. Remember that 2 moles of C2H2 reacts with 5 moles of oxygen to produce 4 moles of CO2. So these are called the molar coefficients. 2 moles reacts with 5 moles to make 4 moles and 2 moles. So if we know the moles of any one chemical, we can solve for the moles of all the other chemicals. So how do we do that? Well, we have a mass of C2H2, so we can turn that into moles using its molar mass. So that's always your first step in Stoich, is find a mass or volume of a chemical and figure out its moles. I'm just going to write down here, we're looking for mass of CO2, and we're going to get that by starting with the moles of C2H2. So I know that I have 30 grams of C2H2, and I can turn that into moles using its molar mass. 2 carbon, 2 hydrogen, 26.04 grams per mole. And I have to flip the molar mass. Why do I have to flip it? So the grams cancel out. Okay. Now, if I stop right now for this question, I have solved for the moles of C2H2. Now, I know that if I have 2 moles of C2H2, I can get 4 moles of CO2. It's a 2 to 4 ratio. So we're going to use that ratio to figure out the exact moles of CO2. So you always put the chemical you're looking for on top, and we use our coefficients from the balanced equation. 4 moles of CO2 are produced for every 2 moles of C2H2. Now, why am I using C2H2 on the bottom? So that I can cancel it out with the C2H2 on the top. Okay, so in this question, I'm going to cancel out everything I can. All right, so what's left? I've got just moles for my unit and CO2. So I have solved for moles of CO2. Hey, that's close. We're looking for the mass of CO2. So my last step is to turn the moles of CO2 into the mass using the molar mass. And CO2 is 44.01 grams per mole. And now the moles cancel out, and we're left with grams of CO2. Plug it all into your calculator, and you get 101.40 grams as the mass of CO2. And we're going to go look at our sig digs. We got 3, 4. These don't count because they're exact numbers, not measured values, so those don't count. 4, 4, and 3. So my final answer needs to have 3 sig digs. 101 grams is the mass of CO2. So that's your review from gravimetric stoich. So now we're going to start on the notes for today from your study guide, gas stoichiometry. And we're going to go through, I think, 3 or 4 problems. And you will be masters of gas stoich, hopefully. Okay. 275 grams of propane burns in a gas barbecue. Okay, so here's another chemical reaction. We've got propane burning. And we're looking for volume of oxygen. Okay. So remember, it's a chemical reaction. We're trying to find out volume of a chemical, starting with a mass. So it's going to be stoichiometry. Okay, stoichiometry means balanced chemical equation. Propane burns. Hopefully you remember the formula for propane, C3H8 gas. Burns means reacting with oxygen. Again, it's a hydrocarbon. It's made up of only hydrogens and carbons. So the products are always going to be CO2 gas and H2O gas for a hydrocarbon combustion. Okay, let's balance it quick. 3 carbons, 8 hydrogens, put a 4 in front, 8 hydrogens. Okay, my hydrogens and carbons are balanced. All I have left is oxygen. 3 times 2 is 6. 4 times 1 is 4. So I have 6 and 4 for a total of 10. Put a 5 in front of there, and now I've got 10 oxygen. So we have a balanced chemical equation. Now we can do our stoichiometry. Okay, so let's start with the chemical that we know we can get the moles of. We have 275 grams of propane. We're looking for volume of O2 gas at STP. I'm just going to put that off to the side. Okay, that's what we're looking for, but we have to start with the chemical that we know its mass or volume, which is propane. 275 grams of propane. Okay, we need to turn that into moles so that we can use these molar ratios or molar coefficients. Okay, 275 grams of propane times its molar mass, and we're going to flip the molar mass. Moles on top, because that's what we're looking for. And we're going to cancel out the grams. C3H8, its molar mass, 3 carbon and 8 hydrogen adds up to 44.11 grams per mole. Okay, and so we can cancel out the grams, and we have moles of propane. Now we want to convert that because the question is asking us for oxygen, not propane. So our molar ratio is 5 moles of oxygen react for every 1 mole of propane. So remember, we are writing the moles of the chemical we're looking for on top, and the one we want to cancel out on the bottom, because you can see now how we can cancel out the propane. Propanes cancel out, and I can cancel out these moles, and what am I left with? Moles of oxygen. Hey, we're close. We want the volume of oxygen at STP. So how do I turn moles of oxygen into volume? Well, remember at STP, the molar volume of any gas is 22.4 liters per mole. So we need this in gas stoich. This is really important for any gas at STP. Oh, that is messy. STOICH. Believe it or not, that says gas stoich. So for any gas stoich problem, if it's at STP, we can use this value. So how would I write that in here? I need to cancel out moles. Let's go orange. Okay, I need to cancel out this moles, and I need liters of oxygen. So where do I put this moles? If I want to cancel this one out, on the bottom, and on the top, 22.4 liters. So the unit we're looking for is in the right spot. We're looking for volume. There it is. Volume or liters of oxygen. And these guys cancel out. Gone, gone. The only units left in here are liters. The only chemical left is oxygen. So when we solve this, we're going to be solving for liters of O2 gas. Plug in everything in the top, divide by everything on the bottom, and you should get 698.254 liters. 698.254 liters. Sig digs. 3, 4. Coefficients don't count. 3, 3, 3, 4. So our final answer is 3 sig digs, which is right there. 698 liters of oxygen. Okay. How's everybody doing? So that's your first gas stoich problem. Half the battle is getting that balanced chemical equation. So on the next one, if you want to get a head start on me, you can pause the video and try and write your own balanced chemical equation, or you can just let me do the work. Doesn't matter. Okay, hydrogen gas is produced when sodium metal is added to water. Sodium metal. That is really messy. I'm writing too fast. Okay. Sodium metal, so solid, is added to water. I'm going to write my water like HOH or as HOH. I like to do it that way because it shows me the H part and the OH. Water often reacts by splitting into an H and an OH. Okay, sodium reacts with water and we produce hydrogen gas, H2. Now we have to produce more than that. This is like a single replacement. So the Na goes with the OH, Na plus and OH minus. NaOH, aqueous. That's an ionic compound in water. So hydrogen gas and sodium hydroxide. Balance it. 1 sodium, 1 sodium, 1 OH, 1 OH, 2 hydrogen, 1 hydrogen in front. So I need a 2. Now that changes. So now I have, just going to underline these, 2 hydrogen there and 2 hydrogen there. I also have 2 OHs and 1 OH. So I need to put a 2 in front. Now I have 2 OHs, but now I've changed the sodiums to 2 sodiums. So I need a 2 there. Okay, there's my balanced equation. That one was tricky. Now that I have a balanced equation, the gas stoich is pretty easy. What mass of sodium, so I'm just going to write mass of Na, is needed to produce 20 liters, and that's supposed to be 20 liters of hydrogen at SATP. Okay, as soon as I see SATP, I should write down my molar volume, 24.8 liters per mole for every gas, including hydrogen. All right, so we are looking for mass of sodium. And in stoichiometry, we start with the chemical that we know its amount, or we can get its amount. So we have 20 liters of hydrogen at SATP. So we can get moles from there. So 20 liters of hydrogen, and its molar volume, I'm going to flip it, moles on top, and that's going to allow us to cancel out the liters on the bottom. Okay, the liters cancel out. So what have I solved for? The moles of hydrogen. How did I get the moles of hydrogen? It's volume times its molar volume. Okay, good. So we have moles of hydrogen, but we're interested in finding the mass of sodium. So we need to convert hydrogen into sodium. So here's our conversion ratio or our molar ratio. We're looking for sodium. We always put the one you want on top. 2 moles of sodium react. For every 1, and that's a 1 in front, for every 1 mole of hydrogen that's produced. Okay, let's do some more canceling. So the hydrogens are now canceled out. Those moles cancel out, and we now have moles of sodium. We're really close because we want the mass of sodium. How are we going to turn moles of sodium into mass? Molar mass. And sodium's molar mass is 22.99 grams per mole. 22.99 grams per mole. Okay, awesome. Plug it all in and away we go. And when you plug it all into your calculator, you should get 37.080 grams for our mass of sodium. And sig digs, 3, 3, 4. So lowest sig digs is 3. So I have to take those 3, the 8 rounds up, so that becomes 37.1 grams solid sodium. Okay, gas Stoich. So this is called a combination problem. It's got a gas, a volume of gas, and we're finishing with a mass of a solid. So we're turning a volume of gas into a mass of a solid. Okay, so I've got 2 left to do. This one you can try and balance on your own if you'd like. So you can pause the video and do the combustion of methane, or you can watch me do it as you fill it into your notes. Okay, so methane is combusting and producing CO2. Methane is 1 carbon, CH4. You need to know that formula. Methane combusts O2 gas to make CO2 and H2O. Always hydrocarbons make CO2, H2O. Okay, 1 carbon, 1 carbon, 4 hydrogen, 4 hydrogen, 4 oxygen, 4 oxygen. That's a nice easy one to balance, and these are gases. Okay. So what are we looking for? What volume of methane? Volume of methane. Okay, it's a Stoich problem. Start with what we have, our amount of chemical. There's our volume of CO2, 50 liters of CO2, and we can turn that into moles because it's at SATP, 24.8 liters per mole. So that's how we can turn liters into moles. Flip it. Moles over 24.8 liters. Okay, liters cancels out, and we get moles of CO2. Good. Okay. Now we want methane, volume of methane. So we're looking for methane, so we need our molar ratio. 1 mole of methane reacts to produce 1 mole of CO2. Okay, this is an easy one, a 1-to-1 molar ratio. CO2 went on the bottom because we want to cancel it out. CO2 is gone. And now we have moles are gone. We've got moles of methane. And we want volume of methane. Well, that's easy. It's still at SAT. Because it's still at SATP, we can turn moles into volume using our molar volume. So now the moles cancel out. Moles are gone, and we are left with liters of CH4. Plug all the numbers in, and you get 50 liters of CH4. Okay, well, that's interesting. Let's turn our brains on for a minute and take a look at this. We started with 50 liters of CO2, and we finished with 50 liters of methane, the exact same volume. If you look at the coefficients, 1 mole of CH4 is the same as 1 mole of CO2. So for every mole of CO2 that I produce, I'm using up 1 mole of methane. Now this rule, so we know these numbers can represent moles. We know that from gravimetric Stoich. But special deal today only, for gases, only for gases, these numbers also represent volumes. So that 1 could also represent 1 liter. And this 1 could represent 1 liter. So what that means is every 1 liter of CO2 that's produced uses up 1 liter of methane. So if we produce 50 liters of CO2, we use up 50 liters of methane because they are a 1-to-1 volume ratio. So these can be molar ratios or volume ratios. That's really important. So it's a shortcut. And you can see it from the math as well, that we can just cancel these two out because they are the exact same thing. So really all you're doing is taking the volume of one chemical using the volume ratio and turning it into the volume of another. So these are really easy questions when it's a gas turning into a gas at the same conditions. So this only works if the temperature and pressure are constant or the same. And they are. This whole question is happening at SATP. So because it's happening at SATP, we can cancel out the SATP's super easy shortcut. Okay, hopefully that makes sense to you. And if it doesn't, you can do it the long way. It's okay to write both of these in and cancel them out. Just use that gas Stoich format. It also works. It just takes a little more time. Okay, I think we only have one left and then we're done. Whoops. Hooray. Here we go. Yep, last one. What mass of CO2 is produced when 20 milliliters of butane gas is burned at SATP? Okay, I'd like all of you to pause the video here, try and balance this equation on your own, and then if you want, even do the Stoich on your own and see if you get the right answer. By the way, this answer is wrong. I believe it is 0.142 grams. Okay, try this one on your own, then come back and see how you did. Okay, I'm going to go through this fast because in theory you've all tried this one on your own. So we get 4 CO2 and 5 H2O, but that doesn't balance nicely, so those are going to need to be doubled. Come on, eraser. Okay. So balanced, it looks like this. That was 8 and 10 H2Os and 13 O2s. Okay, that's your balanced chemical equation. There is no other correct answer. Okay, so we're looking for mass of CO2. And we are starting off with 20 milliliters of butane burned. 20.0. I'm going to leave this as milliliters of butane. C4H10. Okay, so there's my volume of butane. It says STP. There's my molar volume, so I can use that value. Every mole is 22.4 liters. Okay, so 20 milliliters, and I want to cancel out the milliliters, so I put moles on top. 22.4 liters. Now, it is okay to just cancel out the liters and leave the milli. What's going to happen is our final answer will be milligrams because we're solving for a mass. And that's fine. Your answer can be in milligrams. If you want to convert that, it would be 0.0200 liters and go that way instead and have your answer in grams. It's up to you. I'm going to leave it as milliliters and just cancel out the liters. Okay, so I've got moles of butane and I'm interested in CO2. 8 moles of CO2. That's what I'm looking for, and I want to cancel out the butane, 2 moles of butane. Okay, so the butanes are gone, the moles are gone. So what am I left with right now? Millimoles of CO2, and we want mass of CO2. So I need molar mass, which is 44.01 grams per mole. We're looking for grams on top. The moles cancel out. Moles gone. So now my final unit is milligrams, and the only chemical left is CO2. So my answer will be milligrams of CO2. So I do all the math and I get 141.97 milligrams, which is in sig digs is 3 sig digs, 142 milligrams. If we want to convert that to grams, we have to divide by 1,000 milligrams in a gram. And that is the answer you were looking for. And if you started off by putting this as 0.0200 liters, this is the answer you would get in grams. Okay, that's Gas Stoich day 1. Hopefully that wasn't too bad for you. So you have one short assignment to do. It's just 3 questions in your study guide, page 180 if it's Johnson, and I think 184 if you are using Kelly's study guide. 3 questions. Answers will be posted online for you to check your work. Tomorrow you'll get Gas Stoich day 2, and then you'll get a wrap-up assignment and a quiz on Gas Stoich. And that's, so today's Tuesday, then Wednesday. So then on Thursday and Friday, we will start solution stoichiometry. Okay, hope everybody's having a great day. I know it's beautiful weather out there. Finally, spring has arrived. So happy days. Okay, take care, everybody. And I will see you guys super soon.